Hello, Hassler here. We're going to be taking some 3.2 notes on the derivative as a function. And as we work through this, hopefully you're going to see that we are no longer going to depend on those limit definitions of a derivative, but we do have some shortcuts that will give us the same result, the same general slope equation to find the slope of the tangent line at any point for a given function. Okay, so let's run through some notational pieces. Recall from 3.1, we found the derivative or the slope of a tangent line at a specific value using these limit definitions. And I just want to get these down again. F prime of A is equal to the limit as x approaches A of f of x minus f of A all divided by x minus A. That was that first limit definition of a derivative. And the second was f prime of A is equal to the limit as h approaches 0, f of A plus h minus f of A all divided by h. And that's what we just tested on. Okay, and so some notational things. We've talked about this notation of f prime of A, but we haven't talked about anything beyond that in terms of notation that would represent a derivative. And so there are a couple other ways to represent a derivative. So let's say that I have that y is equal to f of x. I could have y equals a function instead of naming the function f of x or g of x or h of x. Okay, then when I'm looking at derivative notation, we talked about this f prime as being the slope of the tangent line. I also could just write y prime. Y prime, that apostrophe it looks like, that notation also indicates the slope of the tangent line. Okay? So again, this represents slope of the tangent line. Now, I may have mentioned, and I forget the things I mentioned in different classes, and I apologize, but there are actually two contributors to the invention of calculus. One of them is Sir Isaac Newton, and he invented calculus in order to do physics, okay? So like side note, I'm going to invent calculus so I can support the physics that I'm trying to prove, okay? And the other was Leibniz, and Leibniz was just purely a mathematician. He was not a physicist. And so he had different notation. And they were simultaneously creating calculus. They had nothing to do with each other in creating calculus, and so, of course, these different notations are going to come to be. And Leibniz notation says, well, if I do have y prime, or slope of the tangent line, I could represent slope of the tangent line using dy over dx. And what this dy over dx represents, the y says, I'm going to take the derivative of the y function, or whatever function I put there. I'm going to take the derivative of y, and the variable in the denominator, this x, represents the independent variable. And while that is typically x, physics people or science people, you know that oftentimes the independent variable in science is time. So you might see something like df dt, okay? Other ways that we can write this notation, y equals dy dx, or sorry, y prime equals dy dx. We could also say y prime equals df dx, right? And so when I say take the derivative of y, or my function could be f, or it could be g, dg dx, okay? Or you could say that y prime is equal to d dx, and then actually write what that function is, f of x. Next to that. We're going to see that notation today as well. Okay? So these are just notational things that you need to be aware of. Okay, so let's talk about some patterns that are going to emerge when we apply these limit definitions of a derivative. So we've done several examples using these limit definitions of a derivative. And one of the examples that we did was saying, hey, if I have f of x is equal to x squared minus 7, and I use my limit definition of a derivative to work through the process, generically speaking, we find that f prime of x, or the equation that would give me the slope of the tangent line to the curve at any x value, we found that just to be 2x. Or the other equation we had was y equals x squared plus 9x. This is one of those practice problems on one of those practice worksheets. And again, you use the limit definition of a derivative. I think this was the second limit definition of a derivative. So you put your a's plus h's, simplified, factor it out an h, blah, blah, blah. And the general equation you found to find the slope of the tangent line was 2x plus 9. Another example we had was that g of x was equal to 3x squared plus 4x plus 2. And again, we worked our magic, okay? We did the second limit definition of a derivative. And what we found is that, again, the formula, I'm actually going to use different notation here. The formula related to the limit definition of a derivative, the formula that popped out to give me the slope of the tangent line for any given x value ended up being 6x plus 4. Now we had a's on our paper. Instead of writing g prime, I'm going to use that Leibniz notation. Another way to represent g prime would be to write dg dx. I'm going to take the derivative of the g function, x is the independent variable. Okay. So if you want, you can say this is the same as writing g prime, just to get yourself comfortable with that notation. And, if we were in class together at this point, I would say, what do you notice? What do you notice as I move from the f function to f prime? Or what do you notice as I move from y to y prime? Or what do you notice as I move from g of x to dg dx? And you would have a conversation with your peers, and you guys would tell me things that you noticed. Because nobody's here to talk to me, I'm just going to have to tell you what I notice. What I notice is that whatever my exponent was becomes the coefficient. Whatever my exponent was becomes the coefficient. Oh, this is interesting. 3, well, and I have this 2. So in order to get to 6, I must have had to do 3 times 2. Okay. Technically, my exponent on this 7 is 0. Well, if I do 0 times negative 7, I get 0. Notice there's nothing written past that 2x. My exponent on on x is 1. And if I do 1 times 9, I get 9. Over here, the exponent on the x is 1. And if I do 1 times 4, I get 4. I guess I could write this as 2x to the 0. And again, 0 times 2 is 0. That's why I have nothing there. So one of the things that occurs to go from my function to my derivative is I take the exponent in the function and I multiply it by the coefficient of that term, and that becomes the new coefficient of my derivative. The other thing that happens is this. I started out with an exponent of 2, and now I have an exponent of 1. I started out with an exponent of 2, and now I have an exponent of 1. I started out with an exponent of 1, and technically, I now have an exponent of 0. Anything to the 0 power is 1. That's why I don't need to write x to the 0. I started out with an exponent of 2, and now I have an exponent of 1. I started out with an exponent of 1, and now I have an exponent of 0. And I don't even have anything here anymore, because the exponent that I did have, 0, when multiplied by 2 gave me nothing. 0 times anything is 0, so it doesn't even matter what my new exponent would be. So I'm going to put this in math vocabulary. I'm going to say for all exponents n, okay, if I am given that f of x is equal to ax to the n, okay, so n is my exponent, a happens to be the coefficient, then f prime of x is equal to, I take the exponent and I multiply it by that coefficient, right? That's what we did up here. Up here in 3, I said my exponent's 2 times 3. That's how I got this 6. Okay? X, and I'm going to subtract 1 from that exponent to get the new exponent. Okay? I'm going to put this in words. Sometimes when we see things in math notation, we're like, what? Okay? I'm going to put this in words. I'm going to multiply. Okay, that says multiply. My little board is not happy with me right now. Okay, I'm going to multiply my coefficient by that given exponent and subtract 1 from the exponent. So that's in words what's happening with my notation up above. Okay. Okay. So now it says use the limit definition of a derivative to find f prime of x, given that f of x equals x squared. Okay, so f prime of x is equal to, and because I'm not given a specific x value, okay, I'm just going to use that second limit definition of a derivative. That means I have to replace x with a plus h squared minus my function. I apologize. I'm going to use x's instead of a's just because they've said find f prime of x. So x plus h minus x squared all divided by h. That's equal to my limit as h approaches 0. When I multiply this out, I get x squared plus 2xh plus h squared minus x squared all over h. My x squareds are going to cancel. So I'm going to get the limit as h approaches 0. I notice that my remaining terms have an h in them. I'm going to factor that h out. I'm left with a 2x plus h divided by h. These h's divide out. I'm applying the limit just to this function, and when I apply the limit, I'm substituting 0 in for h, and I get 2x. I find that f prime of x is 2x. If I start with x squared, then the generic formula to find the slope of the tangent line at any x value would be 2x. If I would have just used the power rule from the beginning and I have that f of x equals x squared, I would have said, well, f prime of x is equal to my exponent, 2, times the coefficient, which is 1, so that doesn't change anything, x to the 2 minus 1. I'm going to take that original exponent and subtract 1. When I clean that up, I get 2x. Oh yeah. Whew, that was so much faster. Okay. And so the idea is now that I have this